Howdy, this is your friendly neighborhood physics teacher here, and we're going to do Unit 6 FRQ on College Board. So this is simple harmonics. This is the last unit we've kind of did. You had to do the notes and PowerPoint on yourself, by yourself. This section isn't very big in the AP test, but it's a good little thing to look at. So we're just going to do question 1. This question is a long free response question. Show your work for each part of the question. And then there's no diagram in this one, which is weird. So in a physics lab, a group of students are provided with a sphere of unknown mass, a roll of string, a ring stand, and measuring devices that are commonly found in a physics lab. The students must graphically determine the acceleration due to gravity near Earth's surface by putting the sphere into simple harmonic motion. A. State a physics principle, law, or equation that the students could use to graphically determine the acceleration due to gravity near Earth's surface by putting the sphere into simple harmonic motion. So let's kind of draw, since it didn't give us a diagram, let's draw our own little diagram. So it said it gave us a sphere of unknown mass, so we have a sphere. And then it says a ball of string, so we can actually, I'm sure we're attaching the sphere to the string since we have to put it into simple harmonic motion. And then it gave us a ring stand. So a ring stand is literally a stand with a ring on it. Woohoo! Ring stand. And then other measuring devices. So other measuring devices is probably a meter stick, a timer. I'm trying to think what else you would need for this one. As of right now, that's the only really 2 things I can think about that you would really need is a meter stick and a timer. And just a reminder what simple harmonic motion is, we did this in energy, our energy unit. And so for a because this you're basically putting into a pendulum. So you have, it goes from here, and then it swings to here, and then it continues swinging to here. And you have this motion going on. It's just swinging back and forth, back and forth. One thing that we didn't really talk about, I think I halfway mentioned, but didn't really talk about, is there is a equation to find the period. Period, if you remember, period is just the time it takes to do one oscillation, one back and forth. And so so to answer part A, so the equation you would use, and this equation is on your formula chart. So the period for a pendulum equals 2 pi square root of L divided by G. That G is your gravitation. That's what these students are trying to solve for, is the acceleration due to gravity. The L is just the length of the string. That's why you need the meter stick. And then remember, period is just how long it takes to do one back and forth. So yeah, you get a point for putting that equation. There's actually no explanation in this one. You just had to put the equation. Not bad. So part B says design an experimental procedure that students could use to graphically determine the acceleration. Now, graphically means like visually. Determine the acceleration due to gravity near Earth's surface by putting the sphere into simple harmonic motion. In the table below, list the quantities and associated symbols that would be measured in the experiment and the equipment that would be used to measure each quantity. You do not need to fill in every row. If you need additional rows, you can add them. And then it goes into, this is where you describe your procedure. So you list your procedure just like you've done on almost every single lab I've made you do. All the labs recently I've made you do. So this one you were able to get, the other one was just 1 point. So you got 1 point for putting the equation. This one you have a chance to get 1, 2, 3, 4, 5, 6 points. And basically you just do step 1, step 2, step 3. So step 1 would, and you have to think about every single thing. So if you want to draw a little diagram to, step 1, secure one end of the string to the ring stand, and secure the other end to the sphere. Let the sphere hang at rest, kind of like what our diagram's doing. Measure the length of the string with the meter stick. So that would give us one of the quantities here. And filling out our little chart up here. So you have quantities being measured would be length of pendulum. The symbol of that would be the little L, and you need a meter stick to do that. Then it goes into using a protractor, raise the sphere while keeping the string taut to a location where the angle between the sphere's new location and its hanging rest position is at or less than 15 degrees. Okay, so you need a protractor. So you would put angle is what you're measuring. That's using a theta, and you use a protractor. Release the sphere from rest. So you have it up. So we're at this stage up here. So we put it up here. So let's add protractor to our mix. Protractor to get the angle. And then use a stopwatch, so a timer of some sort. So timer, it would list timer or time, little t, and then stopwatch timer or something. Record the amount of time it takes for sphere to make 10 complete oscillations. Perform this trial multiple times. Change the length of the string and repeat steps 1 through 6 for at least 4 different lengths of string. The reason you're changing the length, you're seeing if the length of string is going to affect the gravity, because you're trying to solve for gravity. That's the whole point of this lab. So if you're looking at this equation, you need to change your length to see if your gravity stays constant. So there you go. C. The student must graph the data that they have collected so that they can determine the acceleration due to gravity near Earth's surface. Indicate below which quantities would be graphed on the horizontal axis or vertical axis to determine the acceleration due to gravity near the Earth's surface by using a best fit line. You may use the remaining columns in the table above as needed to record any quantities, including units, that are not already in the table. So I'm going to let you know you're not going to get any points for doing this. I mean, I would still do it since it tells you to, but most of the time it's going to be writing your paragraph that's you're going to get points for. So I still use the chart. It's a handy little thing to kind of get your brain together. And C does have multiple parts. So putting down what it's going to be your vertical axis and horizontal axis is just part 1 of 2. Sorry. So again, this comes and you use your equation. You're basing everything off this equation, and this equation is on the formula chart. So that's good. So CI, that's for to compare. So you want to make a linear equation. So we're trying to solve for gravity. Well, if we take that, so if we're looking at the equation, we can take our 2 pi out because those are just numbers. So we can just say that your period of a pendulum is proportional to the square root of L. I literally took that from the equation. And you can do any form or fashion of this. There's all kinds of different ways. That's just the basic you pull from the equation. If you want to get fancy, and I'm looking at the key here, which that's new. They said they would accept. So if you did put the 2 pi if you pulled the 2 pi, so if you took everything but g, they would accept that. And like I said, you can do any variation. So if you wanted to get rid of, so let's say again we ignored the 2 pi and you wanted to get rid of the square root, well, this would become squared, and then that one would be like that. So there's all kinds of variations you can do of this. But I would say the easiest way is just to pull from the equation. And you get 1 point for that. Part 2 of C says the students determine that the slope of the line is m. Derive the equation that can be used to determine the acceleration due to gravity's Earth's surface by using the slope of the graph that is described by the quantity plot from part C1 or CI. Express your answer in terms of slope m and any other fundamental constants. So you're looking at, so again, it goes back to, so C double I, so it goes back to this equation here. So our potential, our pendulum, our period for the pendulum is 2 pi square root of L over G. And you're trying to manipulate to get you're trying, and it says your slope is m. So you're going to end up manipulating it. So let's get rid of this square root. Now remember, you have to square, right? Your square root is squared, but you have to square everything on both sides. So you get a TP equals 4 pi squared of L divided by G. And it says we get it in terms of m. So we're trying to figure out how to put m into this equation. We really are. We're trying to figure out how to put m in this equation. And I'm going to let you know we're going to pull out L. So we're going to move L onto both sides. So we're going to divide, whoops, it's not an L. Nope, that's what, squared. So we're left with period squared over length equals 4 pi squared divided by G. Ouch. So we have now got the slope, right? So it says m represents the slope. We did basically rise over run. So right here, so this is why you need to know the manipulation, because right here we see that that is the thing. So that is just going to turn into m, because that is our slope. And that's what it just states, that our slope is m. And then you have to manipulate it so you can solve for g. So all we're going to do is multiply both sides by g, because we never want what we're looking for on the bottom. So we get g m equals 4, whoops, my 4 looks like a pi, 4 pi squared. And then we're just going to divide by m, which is our slope. G equals 4. My 4 keeps looking like pi's. 4 pi squared over m. So there we go. So you actually got a point for getting this far, and then you got a point for getting this far. So that is part C double I. And we're going to jump to part D. D does have a diagram. And the diagram looks very similar to this little diagram I drew up here. Except these are labeled. So it's going to be labeled X, labeled Y, and labeled Z. It says, in a second experiment, the student attached a sphere to a spring string such that it undergoes simple harmonic motion between points x, y, and z, as shown in the figure. Point x and z are the sphere's maximum displacement from its equilibrium position. Y is at the sphere's equilibrium position. As the sphere swings along its arc, a student cuts the string at point z. Predict the motion of the sphere after the string is cut in terms of the sphere's displacement, initial speed, and acceleration. We kind of did this when we did the circular motion lab, when I had y'all spin around the stopper and then let go. This is basically it. It's just on a it's not a full-on circle scale. It's just a half circle. So you've done this before, just in a different situation. So what's going to happen so it's swinging back and forth, la, 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 and then you have that kid that comes and cuts your string. What's going to happen to the ball? So hopefully you said the ball is going to continue in whichever direction it was going due to inertia, right? So from here, it's going to probably, if it's being released here, it's probably going to do like this, an aspect. Eventually it's going to, I'm just running out of, well, I guess I could have moved a little, but it's going to eventually go down. So your displacement of the sphere will be eventually a vertically downward motion. And the initial speed is going to be 0 at this point. And the reason it's going to be 0 is because it says that it's at its max position. So remember, if you think about the type of energies, this has max gravitation, this has max kinetic, and then again this has max gravitation. So if it's max gravitation, it's only height. There's no velocity, so it's just going to, so your initial velocity is going to be 0. It's just going to go off in the direction that, well, that's if you can cut it right there. So most of the time it's going to do something like that. In theory, if you could get it, it's just going to go down, and it's going to accelerate at gravity, basically at g. So it's going to move a downward motion and accelerate at z, or at g. So that is question 1 done. Oops. Question 2. This question is a short free response question. Show your work for each part. And we do have a graph. I'm not going to draw the whole entire graph. I'm just going to draw like what the graph looks like. You get this nice little U. And it does touch. Hold on. Let's try that again. So it does touch right there. So it goes up to 10. Goes down to 0. This goes down to a negative 0.3, and eventually where it hits is 0, and then it goes to a 0.3. This is spring potential energy. So spring potential energy, and right here is your horizontal position. So we're comparing our spring potential energy to our horizontal position. Remember, our spring potential energy is our 1/2 kx squared. So it says a block of mass 0.4 kilograms on a horizontal surface is attached to a horizontal spring of negligible mass. The other end of the spring is attached to a wall, and there is negligible friction between the block and the horizontal surface. The center mass of the block is stretched a horizontal distance of x 0.25 beyond the equilibrium position and released from rest such that the block spring system undergoes simple harmonic motion. The graph of the spring potential energy of the block spring system as a function of horizontal position of the center of mass of the block is shown. The positive direction is considered to be to the right. So on the grid below, sketch a graph of the force exerted by the spring on the block as a function of the block's horizontal position. So now we need to make a force graph. So, and then what type of, they give you a four-quaded graph. And they tell you that this is force, and this is your horizontal position. And again, with the they give you that 0.3 to 0.3, and here is 0. And they ask how your force looks. Now, your spring force equation is your spring constant times your x. So when your x is 0, your force is going to be 0. So you know that it's going to be 0 here. So as your distance increases, your force increases, which makes sense because you're putting more strain on the spring. So literally, your force graph is going to be a horizontal straight line. It's going to be in the negative when your position is negative. It's going to be in the positive when your position is positive. There you go. It's going to look something like that. Part B. Part B says calculate the period of oscillation for the block spring system. So there's actual math involved on this one. Oh boy. Actual math. This is part B. So it's asking for the, hold on, go back up. It's asking for the period of oscillation. So a spring, if you look on your equations, your period for oscillation is period of a spring equals 2 pi square root of your mass divided by your spring constant. Well, they give you the mass in the problem, so you could just plug in the mass there, but we need to figure out the spring constant. You know, this had to be harder than a two-step problem. And so we can actually use our spring potential equation because we can look at our graph to give what we need for spring potential. So let's get our K by itself. You know me, I like manipulating before I plug in. So we're going to get 2 spring potential, Kx squared. I'm trying to get K by itself. So we get that our spring constant equals 2 our spring potential Kx. If we look at our graph, it says when it's max, it's 10, and it told us that it goes to 0.25. That's what the paragraph at the very beginning says, and that needs to be squared. So we're just going to plug that into our handy dandy calculator, and it gives us about 320. It would be newtons per meter. That's just the units. And then we're going to take this and plug it in up here. So we get that our period of a spring, that's 2 pi, the square root, said our mass was 0.4 divided by 320. Plug that into the handed-in calculator, and you get about 0.22 seconds. And that's our answer. So this was a pure plug and chug. And again, from that was given in the, I can't see that. Let's try that again. So this was given in the paragraph above, this was given in the paragraph above, and this was given into your graph. So you did have to pull some information before. So now let's look at part C. It says a new block of mass 1 kilogram is attached to the spring. The center mass of the block is stretched a horizontal distance of 2.5. So the 0.25 stays the same, but we have a bigger mass, larger mass. No, less mass. Larger mass. Our mass was before was 0.4. Beyond the equilibrium position and released from rest such that the block spring system undergoes simple harmonic motion. Again, simple harmonic motion is just the spring going back and forth, back and forth, back and forth. The grid below represents the kinetic energy of this new spring block system as a function of the horizontal position of the center mass of the block. Sketch the curve of the kinetic energy of the spring block system as a function of the horizontal position. So again, so if we're going back, just like on the pendulum, if we go back to our little pendulum, it was 0 kinetic energy. At the peaks, it's the same thing when you're dealing with a spring. So if you're dealing with a spring, and it's going back and forth, and so let's say this is at equilibrium, okay? And it says it pulls. So you're sitting there, you've pulled your spring. This is at max spring potential. And as it moves, and it gets back to equilibrium, let's say that's, and then this is going to be max kinetic. This is it moves the fastest at equilibrium, because there's no forces on it. It's able just to go. There's nothing counteracting it. But then when it starts to squish, again, it goes to max spring potential because now it's squishing it. And the force goes, it's happy, and then it goes back up to stretching. So it goes back and forth. So we are going to have some type of curve. So this is kinetic energy. And they have this already horizontal position. Then it goes up to 10 to 0, and it goes to, again, about negative 0.3 to 0.3. So at the 0.3s, it's going to be 0. At 0, which it does have marked, so at 0, it's going to have its max kinetic energy. Now, to figure out its max kinetic energy, you have to think about what would be its max spring potential. Well, we figured out its spring potential in our problem before. Its spring potential, our spring potential is given to us in the graph ahead. And your spring potential is only affected by the spring and how far you stretched it. It's not affected by the mass. So if you only change the mass, it's not going to change anything about your energy. So you're going to go about to 0.25. At 0, you're going to hit 10. You're going to go back down to 0 at 0.25. There you go. Woohoo! And you got 2 points for drawing that graph. Yay! So that is it for our simple harmonic motion. Hopefully, we have technically done this before in our energy unit at the beginning of the year. So hopefully most of this is a review. If you have any questions, please let me know. Remember, you're loved and appreciated. Bye.